Yes, my dear students, this is our third problem related to finding eigenvalues and eigenvectors. Okay, so I have started with again one non-symmetric matrix, and for example, you see that I have written the question as find eigenvalues and eigenvectors of the matrix 6 minus 6 5, 14 minus 13 10, 7 minus 6 4. Now we'll start with the same how to find out the eigenvalues and eigenvectors. I'm going to start with the same procedure. So by showing some 4 or 5 to 6 problems of the different nature, how to find out the eigenvalues and eigenvectors, you will come to know thoroughly how to find out this concept. So we started with the characteristic equation of the matrix is, as usual, determinant A minus lambda is equal to 0. Okay, so here I have written that matrix as, so it is a determinant, so it should be, you have to be very careful, you should not make it as a matrix. So along the diagonal, so you see that along the diagonal 6 minus lambda minus 13 minus lambda and 4 minus lambda I have written in A minus lambda is equal to 0, and the remaining element as it is. Okay, this is equal to lambda cube minus s1 into lambda square plus s2 into lambda minus s3. So if this is your sum of the leading diagonal elements, so it is nothing but your A11, okay, so A22, A22 plus A33. Okay, so it is 6 minus 13 plus 4 is equal to minus 3. Now the second one is, as usual, it is the sum of the minors of the leading diagonal elements. So as usual, for the first leading diagonal element, you have to delete this. I have written minus 13, 10, minus 6 and 4. Okay, and for the second one, and for the second leading diagonal element, it is a 13, so you have to delete the respective row and column, write the remaining elements. It is 6, 5, so I made a mistake here, so you need to rub it off and write it as 5 here. Okay, so 5 and 7 and 4. Okay, then plus the third one is the third leading diagonal element is 4, so you delete respective row and column and write it as 6 minus 6, 14 and minus 13. Okay, so now we are going to find out these minors value and then by adding it. So it is minus 13 into 4, then minus of minus plus 6 into 10, so it is 60, minus 52, 60, I have written it as 8. Next one, 6 into 4, 24, then 7 into 5, minus 35, so 24 minus 35, I got it as minus 11. And next one is minus 78, that is 6 into minus 13, it is minus 78, then minus of minus plus 14 into 6, it's 84. So you got it as minus 11, 8 plus 6, 14, 14 minus 11 is equal to 3. So your S3 is now, it is a determinant value of A, so which is equal to determinant E6 minus 6, 5, 14 minus 13, 10 and 7 minus 6, 4. Okay, it is equal to 6 into, so determinant also you know that, but anyhow once again I'll explain you for this problem. So I have to delete this respective row and column, write the minor, minus 13, 10, minus 6 and 4. Okay, so the next one is minus times this middle element, so you just delete the respective row and column. 6 into the 2 minus of minus 6, it becomes plus 6, 6 into 14, 10, 7 and 4, so I have written here. Then the next one is the last element, which is 5, So you have to delete the respective row and column, write the remaining determinant. So it's 14 minus 13, 7 and minus 6. Is it clear? So I have to find out now based on that the determinant value. So I got it as here 6 into minus 52 plus 60, so it is 8. 6 into 56 minus 70, it is minus 14. 5 into minus 84 plus 91, 7. So by multiplying it 6 into 8, we have 48. 6 into minus 14, it is minus 84. 5 into 7, 35. So by adding this, we got it as minus 1. So our characteristic equation is therefore, it is minus S1 times lambda square. So what is S1? Minus 3. So minus of minus, it becomes plus 3 lambda square plus times S2. So S2 we are getting it as 3. So 3 into lambda plus minus times the constant term. So already minus 1 is there. So minus of minus plus. So I told you that's why the forming of characteristic equation is very, very important in this problem. If you miss even a positive sign or a negative sign here, you never get a correct eigenvalues, then automatically the entire problem will be wrong. Okay. So that's why I have taken here to explain you every time the shortcut method in detail. So that shortcut method is very easy, and directly expanding that determinant value, it takes time, and by expansion of so many lambda coefficient and lambda square, lambda cube, it leads to so many mistakes. If you miss even one value, you may make mistakes. So that's why you have to be very careful in calculating this characteristic equation. So now the characteristic equation is lambda cube plus 3 lambda square plus 3 lambda plus 1 equal to 0. Now we are going to find out the lambda value. I have not shown you the synthetic division, so it's better I'll show you in the last portion, because I forgot to include that synthetic division. So I'll write the equation, I'll show you the synthetic division in the last page. What is the equation is, we got it as here lambda this the equation is lambda cube plus 3 lambda square plus 3 lambda, all are positive. Okay, so I'll show you here now how to write it. So it is lambda cube plus 3 lambda square plus 3 lambda plus 1 equal to 0. Okay, so I'm going to start with writing the synthetic division. So I told you already that you need to write the coefficient only. Okay, if any of the coefficient is missed, don't forget to put that coefficient in the place of coefficient as 0, otherwise the calculation will be wrong. Now I have given that it's minus 1, it suits the problem, so let me check with it. So minus 1 into 1, we have minus 1, 2, minus 1 into 2, we have 2, minus 2, 3 minus 2, 1, so 1 into minus 1, minus 1, so automatically you are getting it as 0. Is it clear? Similarly, the next value also I have given you as minus 1. So let me start with 0. 1 plus 0, 1. 1 into minus 1, minus 1. 2 minus 1, 1. So 1 into minus 1, minus 1. So this is also 0. So how can I write? First two values are here, like minus 1. And lambda 2 is also equal to minus 1. Lambda 3, how can you write? This is the equation. So this is the coefficient of lambda. This is constant term. So it's lambda plus 1 equal to 0. And here also, your third value is also minus 1. So it is a completely different problem where this is a non-symmetric matrix, but all the three eigenvalues are same. So we are going to check how to find out the eigenvector. Okay, so let me go to the now first one. I have shown you how to find out the eigenvalues. So here we are going to start with eigenvector. So all the three eigenvalues are same. So your calculation of this A minus lambda into X matrix will be the same. So all the three equations will be same only. So now you see that it is 6 plus 1 minus 6, 5, 14 minus 13 plus 1, 10, 7 minus 6, 4 plus 1 into x1, x2, x3 equal to 0. So your equation, you see that 7x1 minus 6x2 plus 5x3 is equal to 0, 14x1 minus 12x2 plus 10x3 is equal to 0, 7x1 minus 6x2 plus 5x3 is equal to 0. So if you are observing that all the three equations are same, so we can't solve by cross-road multiplication and no other way. So that's why I have written we have to discuss about this eigenvector in a different way. I mark that entire system as 1. In a system 1, first and the remaining two equations are same. So the only way of finding the eigenvectors are assign always let x1 equal to 0, find the remaining 2. And let x2 is equal to 0, find the remaining 2. And let x3 is equal to 0, then find the remaining 2. So I started with putting x1 equal to 0, so that the entire, any equation you can take among 3. So I have written the equation, I put x1 equal to 0. So you'll get the remaining equation minus 6x2 plus 5x3 is equal to 0. So you get minus 6x2 is equal to minus 5x3. So minus both get cancelled. We'll get x2 is equal to 5 by 6x3. So I told you already that whenever you are going to write your eigenvector should be always numerically very less value. How far it is possible for you to assign eigenvector as a very small numerical value, that is always better for your calculation. So that's why you see that it is in a fractional value. I can't assign any x3 is equal to 1 numerical value, so that your x2 will get it as a fractional value. So I won't prefer that. It is better always you keep it as a real numbers. Okay. So what I am going to assign is x3 is equal to 6 I am going to give, so that the 6 and 6 get cancelled. So you will get it like this. That is 5 by 6 into x3 is also 6, means 6 get cancelled, you will get x2 equal to 5. So that's why we are getting it as the eigenvector. For x1 equal to 0, you are getting it as x2 is equal to 5 and x3 is equal to 6. So therefore, this value is x1, first vector is 0, 5 and 6. Is it clear? Similarly, we are going for finding by assuming x2 is equal to 0. So when x2 is equal to 0, same equation I have taken, you put x2 is equal to 0 here, this will vanish. You write the remaining 7x1 plus 5x3 is equal to 0, 7x1 equal to minus 5x3, x1 equal to minus 5 by 7x3. Here also it is optional arbitrary value you have to put. So what I have taken as usual, 7 I have taken. So 7 get cancelled, you will get a minimum value. So your x3 is equal to 7 means x1 equal to minus 5 good. So that is another vector. So minus 5, 0, 7. This is the methodology you can use only for the non-symmetric matrix. We can't use this methodology for symmetric matrix. Okay. Now the next one, you substitute x3 is equal to 0. So the same equation of substituting x3 is equal to 0 will have only x1 and x2. So 7x1 minus 6x2 is equal to 0. So 7x1 is equal to 6x2. Therefore x1 is equal to 6 by 7x2. So now you can tell automatically what is x2 value. x2 value is 7. So x1 equal to 6 you will get. So therefore your x3 is equal to 6, 7. Assumed already x3 is equal to 0. So it is 6, 7, 0. Is it clear? So this is entirely a different problem. It is not at all compared with the previous two problems what I have given. This is entirely a different problem where all the three eigenvalues are same, but you see the vectors how it looks like. x1 equal to 0, here x2 equal to 0, and here x3 equal to 0, and these are all the three eigenvectors. We got it, different eigenvectors for the non-symmetric matrix. Is it clear? So the another one more thing you need to be very careful here, it is you have to remember if all the three eigenvalues are same, especially for the non-symmetric matrix, you need to find out the eigenvector only by this method only. Okay, provided if all the three equations are same, then this is the methodology. Suppose if you are not getting all the three equations are same, if you are getting a different equations, that case is different. Okay, so you can solve any one vector by solving by cross multiplication method. The other one you can give like these two options. Okay, so we'll if time permits, we'll go for that type of problem also in the next class. So here I have given here just the same eigenvalues with the eigenvector. Okay, how the distinct eigenvector, infinite number of eigenvectors we can find out. Is it clear? Okay. So you note this synthetic division also. This is the way we have to find out the synthetic division. So I think by observing this, you get a clear idea about the synthetic division also.